Hello and welcome back. In today's video, I'm overclocking the Intel Core Ultra 9 285K all the way up to 5.8 GHz using the Asus ROG Maximus Z890 Apex motherboard and custom loop water cooling. I do that by using most of Arrow Lake's fundamental overclocking technologies, which I discussed in previous videos already. This is probably the most extensive tuning I've ever done with a CPU. In this video, I break down the Core Ultra 9 285K tuning process into 6 unique overclocking strategies for beginner and advanced overclockers. Anyway, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that I'll be using in this guide, as well as the stock performance. The Intel Core Ultra 9 285K is part of Intel's Core Ultra 200S product line, codenamed Arrow Lake. The Core Ultra 9 285K succeeds the 24-core Raptor Lake Core i9 14900K, which we overclocked in SkatterBencher number 67. It has a P-core base clock of 3.7 GHz and a listed boost frequency of up to 5.7 GHz. The E-cores can boost up to 4.6 GHz. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we need to check what is the performance at default settings. Intel defines 3 power profiles for the Core Ultra 9 285K: baseline, performance, and extreme. For the purpose of this guide, we follow Intel's direction and rely on the performance profile for the default settings. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. Here are the OCCT benchmark scores at stock. Here are the ADA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5191 MHz with 1.123 volts, and the average CPU E-core effective clock is 4427 MHz with 1.033 volts. The average CPU temperature is 85 degrees Celsius. The average CPU package power is 247.7 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5208 MHz with 1.132 volts, and the average CPU E-core effective clock is 4600 MHz with 1.034 volts. The average CPU temperature is 80 degrees Celsius. The average CPU package power is 246.2 watts. Of course, we can increase the performance by unlocking the power limits and overclocking our CPU, and that's exactly what we'll do in the coming overclocking strategies. But first, make sure to locate the CMOS clear button. Pressing the clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In the first overclocking strategy, we rely on Asus's advanced OC profile, multi-core enhancement, and Intel XMP technology. As I mentioned earlier, Intel has clarified the rules of engagement when it comes to the default BIOS setting. So it has imposed stricter regulations of what can be the default settings on a motherboard. On the one hand, that creates a little bit more restriction, but on the other hand, it also opens up the field for innovation from the motherboard vendors. The Asus Advanced OC profile sets up the BIOS so it's ready for overclocking. Not only does it reconfigure some of the parameters included in Intel's default profiles, but it also configures a number of other settings related to power saving, performance limiters, and so on. Most importantly for our guide, however, you're required to switch to the Advanced OC profile for any kind of overclocking. Intel Turbo Boost 2.0 technology allows the processor to run faster than the base configuration when it's operating within temperature, power, and current limitations. The obvious advantage is improved performance in both single-threaded and multi-threaded workloads. The Turbo Boost algorithm works according to an EWMA formula. This stands for exponentially weighted moving average. There are 3 main parameters to consider: PL1, PL2, and tau. Turbo Boost 2.0 technology has evolved over the past years to incorporate a lot of power, thermal, and electrical performance limiters. An easy ASUS multi-core enhancement option on ASUS motherboards allows you to unleash the Turbo Boost power limits. Enabling ASUS multi-core enhancement adjusts the following parameters. Intel XMP 3.0 is the new XMP standard for DDR5 memory. It was introduced alongside the Alder Lake processor in 2021. It's largely based on the XMP 2.0 standard, but it has additional functionality. The XMP 3.0 standard is designed with 6 sections. One global section, which describes the generic data that is used across all the profiles, and then the 5 other sections are designed for 5 XMP profiles respectively. Each profile has a wide range of configurable fields related to voltage, frequency, and memory timings. XMP allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports XMP, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. It's the first time that I'm using this DDR5 8400 kit in any overclocking guide, so it's brand new to me. Unfortunately, I wasn't able to run it at 8400 out of the box, and I had to reduce the frequency to DDR5 8000 while retaining all of the other XMP parameters. Upon entering the BIOS, the CPU boost frequency with one active P-core is 5.7 GHz. The average boost frequency gradually trails off to 5,400 MHz when all P-cores are active, and to 4,867 MHz when all P and E cores are active. The 2 favored P-cores can boost to 5.7 GHz, the 6 other non-favored cores can boost to 5.4 GHz, and every E-core can boost to 4.6 GHz in single-threaded workloads. We reran the benchmarks and checked the performance increase compared to the default operation. The Core Ultra 9 285K is the most powerful of all Arrow Lake K-SKU processors and thus limited by power and memory performance. By unlocking the power limits and enabling XMP, we get a nice uplift across the board, especially in multi-threaded, memory-hungry applications like Y-Cruncher and AI Benchmark. The GeoMean performance improvement is plus 3.83%, and we get a maximum improvement of plus 34.99% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5,297 MHz with 1.157 volts, and the average CPU E-core effective clock is 4,601 MHz with 1.047 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 297.9 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5,293 MHz with 1.148 volts, and the average CPU E-core effective clock is 4,586 MHz with 1.046 volts. The average CPU temperature is 85 degrees Celsius. The average CPU package power is 275.4 watts. In our second overclocking strategy, we finally get to overclock the CPU cores, and we do that by relying on 2 foundational Intel overclocking technologies: turbo ratio limits and adaptive voltage. Intel turbo ratio limit is an Intel technology that regulates the CPU frequency based on how many cores are active. It's called a limit because it literally limits the frequency the CPU can boost to. The tool is pretty flexible and can be configured for various scenarios. The ratio limits are defined in the processor's machine-specific registers, or MSRs, by 2 parameters: the turbo ratio limit and the number of active cores. Furthermore, on hybrid designs like Alder Lake, Raptor Lake, or Arrow Lake, the configuration of the P cores and the E cores are independent. In other words, the applied ratio limit for the P cores is independent from the limit of the E cores. Note that configuring the turbo ratio limit is not the same as setting a per core ratio. When we use the turbo ratio limit, it means that we're defining the frequency as a function of how many cores are active. Per core ratio limit is an Intel technology that allows you to set a maximum frequency on a per core basis. It's based on the Intel Turbo Boost Max 3.0 technology that was launched alongside Broadwell E in 2016. Basically, this limit allows you to prevent CPU cores, specific cores, from boosting higher, even if the turbo ratio limit would allow it. The per-core ratio limit plays an important role in the Arrow Lake overclocking process. It's not only the ratio used in the VF point configuration, but also the ratio referenced by many other ratio tuning technologies. The voltage regulation for the P and E cores is a little bit more complex on Arrow Lake than it was in previous architectures. And that's because Intel has introduced the Digital Linear Voltage Regulator, or DLVR. The external VCCIA motherboard voltage regulator, or MBVR, provides the input voltage for the individual P-core, E-core clusters, ring, last level cache, and E-core L2 cache. Each P-core, E-core cluster, and ring has an individual digital linear voltage regulator between the VCCIA voltage rail and the IP blocks. That means each of the blocks can operate at its own voltage. The DLVRs can also be bypassed. In that case, the IP blocks are running in so-called power gate mode, or PG mode. We'll cover that later in this video. Each P-core and E-core cluster also has its own VF curve, which is defined by 9 VF points for the P-core and 7 VF points for the E-core. Here's the aggregate P-core VF curve for my specific Core Ultra 9 285K. The voltage is about 718 mV at 800 MHz, then increases to 1.025 volt for VF.4 at 4.8 GHz, and ultimately ends at 1.385 volt for VF.9 at 5.7 GHz. Each P-core has a different fused voltage for VF.6, which ranges from 1.266 volt for Core 1 to 1.324 volt for Core 4. We need to make a special note about the non-favored P-cores. While it may seem from the graph that they have independent values, that's not entirely correct. And it's quite complicated, because on older decode, the non-favored cores have predefined values for VF.7 and 8, which is determined by the lowest value of the respective favored core VF points. On newer decode, the favored cores don't have predefined values, meaning their VF curve ends at VF.6. For this particular system, we're using the older decode. Here's the aggregate E-core VF curve for my specific Core Ultra 9 285K. The voltage is about 659 mV at 800 MHz, then increases to 762 mV for VF.4 at 3 GHz, and ultimately ends at 1.166 volt for VF.6 at 4.6 GHz. Each E-core has a different fused voltage for VF.6, which ranges from 1.07 volt for E-core clusters 0, 1, and 3 to 1.078 volt for E-core cluster 2. Based on the VF curve, the CPU cores request an operating voltage using the ISVIT protocol from the CPU Power Control Unit, or PCU. The PCU in turn configures the VCCIA voltage rail and the individual DLVRs. There are two ways to configure the DLVR voltage: adaptive mode and override mode. We can configure override and adaptive modes directly in the PCU by specifying a target voltage and a voltage offset for each mode. In adaptive mode, the target voltage is mapped to a core's OC ratio. Each P-core and E-core cluster has its own OC ratio, which is defined by the per-core ratio limit. This also matches VF.9 for the P-cores and VF.7 for the E-cores. You can configure the adaptive voltage and OC ratio to any value. However, multiple rules enforce what ratio and voltage are actually set. Rule number 1. The voltage set for a given VF.n must be higher than or equal to the voltage set for VF.n-1. That means the voltage for the OC ratio, matching VF.9 for the P-cores, must be higher than or equal to the voltage for VF.8. For example, let's say you set the P-core per core ratio limit to 59x and the adaptive voltage to 1.1 volt. In that case, VF.9 will be programmed to 59x at 1.1 volts. However, the actual frequency will be 5.9 GHz with 1.385 volt, as that's the voltage for VF.8. Even if you set the voltage lower in the BIOS, the PCU will override your configuration if it doesn't follow the rules. Rule number 2. For ratios between the OC ratio and the next highest factory fused VF point, the voltage is interpolated between the set adaptive voltage and the factory fused voltage. Let's say we configure the P-core VF OC point to 60x and 1.5 volt. The target voltage for each P-core ratio between 57x and 60x is now interpolated between the P-core's factory fused voltage for 57x and the set adaptive voltage for 60x. There are several ways to configure the adaptive voltage, including setting it for each P-core and E-core cluster individually. In this OC strategy, we set a single global adaptive voltage that's used for every core's OC ratio. Thermal velocity boost is an Intel technology that leverages the fact that CPUs need less voltage to operate at a given frequency when the operating temperature is lower. On CPUs like the Core Ultra 9 285K, Intel uses that idea to reduce the operating ratio when the operating temperature exceeds a certain threshold. For the Core Ultra 9 285K, the default thermal velocity boost configuration decreases the turbo ratio by 1 bin when 2 or more P-cores are active and running above 70 degrees Celsius. For example, the default P-core turbo ratio when all 8 cores are active is 54x. However, it'll downclock to 53x when the operating temperature exceeds 70 degrees Celsius. We can see this behavior in the OCCT results from the previous OC strategy where, despite temperature and power headroom, the P-core frequency is limited to 5.3 GHz. We can easily disable this behavior through OCTVB configuration by forcing the downbin to 0 regardless of the TVB configuration. As I mentioned before, thermal velocity boost is a technology that leverages the fact that you need less voltage to run a certain frequency when the temperature is lower. And the voltage optimizations, or TVB voltage optimizations, will automatically reduce the operating voltage when the operating temperature is lower. For example, for my Arrow Lake launch content, I collected data for the Core Ultra 9 285K to illustrate this behavior. As you can see from the data, with the P-cores at 5.4 GHz, the operating voltage is 1.237 volt when the temperature is below 50 degrees Celsius. However, it increases to nearly 1.3 volt when the temperature approaches 100 degrees Celsius. If you want manual control over the operating voltage to ensure stability, like when you're trying to overclock, it's prudent but not mandatory to disable this function. The manual tuning process for a Core Ultra 9 285K can become quite convoluted because there is a wide range of applications that we need to tune for, from light single-threaded workloads all the way to heavy all-core workloads. Furthermore, as you'll find out throughout this guide, the overclocking headroom of this CPU isn't that great. But anyway, let's try overclocking it anyway, right? We will break down the overclocking process into 3 steps: choosing the voltage, checking per core stability, and then checking all core stability. Usually I determine an appropriate starting point for the adaptive voltage by looking at what is the standard voltage that the CPU will boost to, and then just add 50 to 200 millivolt on top of that. However, this Core Ultra 9 285K doesn't seem to scale very well with voltage. So instead of increasing the voltage, I just stick with the standard VF curve and see how much more frequency I can squeeze out of it at the default voltages. Side note, to avoid the motherboard auto rules configuring the voltage for you, you can set the adaptive voltage to 0.6 volts. For the E-cores, the default maximum voltage is pretty low at 1.07 volt, so I increased the adaptive voltage to 1.25 volt. Note that we want full control over the effective voltage, so make sure to disable any technologies that might adjust the operating voltage, such as the TVB voltage optimizations or advanced voltage offset. After you've set your target adaptive voltage, you can find the maximum stable frequency for each P-core and E-core cluster at that voltage. The easiest way to do that is by setting the turbo ratio limit to, for example, 60x, and then setting the per core ratio limit to the frequency you want to test. For example, a starting point of 57x for the P-cores and 48x for the E-cores. Now you can run a stress test of your choice. I typically rely on the OCTVB CPU stress test, which has a built-in core cycling function. But you can also run a custom application like Core Cycler or pick a different test altogether. You can start with a 30-second quick test first to quickly find the upper limit, and then longer test times to confirm stability. Strangely enough, for the Core Ultra 9 285K, I find that AI benchmark is the most difficult benchmark to pass with a high per P-core core ratio limit, despite it being a multi-threaded benchmark. I attribute this to the benchmark being a highly transient, memory-dependent AVX workload, and it seems that the combination of a demanding workload and a dynamic power profile is the main constraint for stabilizing the high frequencies. The E-cores behave much more consistently, so I don't see the same instabilities in AI benchmark. Finally, we need to check if the CPU is also stable in non-single thread workloads. The easiest way to do this is by running your worst case all-core workload, which in my situation is always 30 minutes of OCTVB CPU AVX2 stability test. You'll typically find that the CPU cannot run an all-core workload at the same frequency as it can run single-threaded workloads. If that's the case, simply lower the turbo ratio limit for all core workloads until it's stable. In addition to the OCTVB CPU AVX2 stability test, I generally also include 3 other workloads during all-core testing: Y-Cruncher, Cinebench R23, and AI Benchmark. While these 3 tests are no replacement for the worst-case stress test, they highlight different kinds of instabilities, usually related to transient loads. Sticking with the factory-fused VF curve for the P-cores, I could increase the non-favored P-cores to 5.6 GHz. The favored P-cores, however, have no overclocking headroom. I could also increase the all P-core turbo ratio limit by 100 MHz to 5.5 GHz. With 1.25 adaptive voltage for the E-cores, I could increase 3 E-core clusters by 600 MHz to 5.2 GHz, while the other cluster could only hit 5.1 GHz. In all core workloads, the maximum stable E-core frequency is 4.9 GHz. Upon entering the BIOS, The CPU boost frequency with one active P-core is 5.7 GHz. The average boost frequency gradually trails off to 5,500 MHz when all P cores are active, and to 5.1 GHz when all P and E cores are active. In single-threaded applications, 2 P cores can boost to 5.7 GHz and 6 can boost up to 5.6 GHz. 3 E-core clusters can boost to 5.2 GHz and 1 to 5.1 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While the P-core overclocking headroom is very limited, we are able to squeeze the E-cores for more performance. Overall, however, the frequency increase is not that much, and that also translates into a not so great performance improvement. The geomean performance improves by another 2.12 percentage points, and we get a maximum improvement of plus 31.26% in PY prime. When running the OCTVB CPU AVX2 stability test, the average CPU P-core effective clock is 5,388 MHz with 1.257 volts, and the average CPU E-core effective clock is 4,901 MHz with 1.172 volts. The average CPU temperature is 105 degrees Celsius. The average CPU package power is 357.0 watts. When running the OCTVB CPU SSE stability test, the average CPU P-core effective clock is 5,489 MHz with 1.242 volts, and the average CPU E-core effective clock is 4,834 MHz with 1.172 volts. The average CPU temperature is 105 degrees Celsius. The average CPU package power is 369.5 watts. In the third overclocking strategy, we delve into tuning the data fabric, which consists of the ring, the NGU, and the D2D. The ring fabric provides the data fabric interface between the various compute IP blocks in the compute tile, the last level cache, and the SoC compute D2D interface. The ring reference clock frequency is generated internally by the CPU PLL. This clock affects all IP blocks in the compute tile, including the P cores, the E cores, and the ring. This PLL can be linked to the SoC PLL when you run in synchronous mode, or work independently if you run in asynchronous mode. The reference clock is multiplied by the ring ratio to achieve the final clock frequency. The voltage regulation for the ring is a little bit more complex on Arrow Lake than it was on previous generation Intel processor, and that's because of the introduction of the DLVR. As we discussed earlier in the guide, the external VCCIA motherboard voltage regulator, or MBVR, provides the input voltage for the DLVRs of the individual P-core, E-core clusters, ring, last level cache, and E-core L2 cache. The DLVRs can also be bypassed, and we'll have a look at that in our final overclocking strategy. The Core Ultra 9 285K ring has its own VF curve, which is defined by up to 9 VF points. The first 8 VF points are factory fused, and the last point is mapped to the OC ratio. Oddly enough, while the default ring frequency is 3.9 GHz, the VF curve is actually defined up to 4 GHz. Here's the ring VF curve for my specific Core Ultra 9 285K. The voltage is about 821 mV at 800 MHz, all the way up to 3.4 GHz, then increases nearly linearly to 1.166 volt for VF.8 at 4 GHz. Similar to the P cores and the E cores, the ring requests an operating voltage using the SVID protocol from the CPU Power Control Unit, or PCU, based on its VF curve. The PCU in turn configures the VCCIA voltage rail and the individual DLVRs. The voltage configuration of the ring is identical to that of the P cores and the E cores, so we both have adaptive voltage as well as override mode. And the rules for adaptive and override mode are also the same. NGU stands for Next Generation Uncore and is the successor to the Uncore that we know from previous generation Intel processors. The NGU consists of a number of different parts, most importantly the network on chip, or NOC, and it's actually the NOC that we're overclocking when we're changing the NGU ratio. The NOC fabric is the primary communication bridge between the various IP blocks on the chip, such as the memory controller, the CPU cores via the D2D interfaces, the graphics, and so on. The NGU reference clock is generated internally by the SoC PLL. However, it can also be clocked with an external clock generator providing the reference clock for the SoC PLL. This clock affects nearly all the IP blocks of Arrow Lake except for those in the compute tile and the PCIe DMI links. The reference clock is multiplied by the NGU ratio to achieve the final clock frequency. The external VCC-SA motherboard VR powers several parts of the SoC dielet, including the NGU. Unlike the compute IP, the parts of the SoC dielet are not powered using DLVR, so power delivery is identical to previous architectures. The voltage configuration of the VCC-SA voltage rail is rather complicated. Since multiple IP domains share the voltage rail, the VCC-SA voltage is set based on the highest requested voltage from the various connected IP blocks. The NOC has its own VF curve, which is defined by up to 4 VF work points. The first 3 work points at 11x, 23x, and 26x are factory fused, and the last point is mapped to the OC ratio. Based on the work points, the NGU requests an operating voltage from the VCC-SA voltage rail using the SFIT protocol. However, there's a second way to voltage configuration. Ignore the SFIT voltage requests and calculations and program the VCC-SA voltage regulator directly over PM bus. This process effectively allows us to take full control over the voltage set by the VCC-SA voltage rail. D2D stands for die to die, and it's the interfaces that connect the various tiles on our Arrow Lake CPU. On Arrow Lake, there are a total of 3 D2D interfaces. On Arrow Lake, only the SoC compute D2D can be overclocked. The D2D reference clock frequency is generated internally by the SoC PLL. However, it can also be clocked with an external clock generator providing the reference clock for the SoC PLL. The reference clock is multiplied by the D2D ratio to achieve the final clock frequency. The default ratio is 21x, which yields a 2.1 GHz operating frequency. The maximum configurable ratio is 40x. The frequency can only be set at boot and cannot be changed in the operating system. The external 0.77 volt VNN AON voltage rail powers several internal voltages, including the D2D interfaces. The VNN AON voltage is pretty important for Arrow Lake CPUs as it is part of the voltage multiplexer for many IP blocks, including the cores and ring, typically serving as the floor voltage in power-saving scenarios. I don't recommend increasing the VNN AON voltage above 1 volt because it doesn't really add that much overclocking headroom, and elevated VNN AON voltages can sometimes cause some issues when trying to cold boot the system. Fortunately, ASUS has included an option called High D2D Cold Boot Workaround in the BIOS that can help alleviate some of the booting issues with increased VNN AON voltages. Tuning the data fabric is a matter of testing each component systematically. I suggest you first pick the voltages that you'll want to use for each of these different components, and then try increasing the frequency one by one. The initial test can be very quick. For example, I'll run a 30-second cycle of Y-Cruncher FFT component tester to find the initial upper limit for each component. When I know the upper limit, I'll set all target ratios and do longer stints of stability testing, including the introduction of other tests. I find that typically Cinebench R23, Y-Cruncher Benchmark, and Component Tester and AI Benchmark are very sensitive to data fabric overclocking. This process might take quite a bit of time, especially if you're trying to squeeze every little bit of frequency out of the different components. Of course, once you're satisfied with stability testing, it also needs to pass all of the benchmarks that we're using in this guide. Ultimately, I ended up with a 4.2 GHz ring, a 3.4 GHz NGU, and a 3.8 GHz D2D. I want to emphasize a particular aspect of ring overclocking, and that's the limited headroom, because I've received quite a bit of questions about it. If you don't see the ring scale with voltage, that's normal. If you don't see a lot of overclocking headroom, that's also normal. The 4.2 GHz that I've achieved with this particular CPU is about what you'll get for a 285K. With a 245K, you can get a little bit extra, just like I showed in SkatterBencher number 83, where I overclocked it to about 4.4 GHz. Upon entering the BIOS, We reran the benchmarks and checked the performance increase compared to the default operation. The multi-tile Arrow Lake architecture adds some layers of communication between the system memory and the CPU cores. By increasing the frequency of the ring NGU D2D, we aim to increase the data transfer speed. We can see that the performance improves accordingly, especially in memory-sensitive workloads. The geomean performance improves by another 1.23 percentage points, and we get a maximum improvement of plus 40.89% in PY prime. In the fourth overclocking strategy, I try to squeeze as much as I can out of the P cores and the E cores. For that, I try to use the most advanced overclocking tools available for Arrow Lake, including the granular ratios, voltage limit overrides, thermal velocity boost, and advanced voltage offset. To safeguard the processor, Intel has, for the very first time, imposed very strict voltage limits for various parts of the Arrow Lake CPU. By default, the voltage limit for the P cores and the E cores is plus 200 mV above the lowest VID for the P cores VF.8 and E cores VF.6. For this CPU's P cores, that would be 1.581 volt. However, we can manually increase that to plus 300 mV under ambient conditions, so 1.681 volt for the P cores and 1.37 volt for the E cores respectively. Granular ratios is a brand new overclocking tool for Arrow Lake processors. It allows you to configure the CPU ratio in steps of 16.67 or 33.33 MHz. The granular ratios can only be configured in reference to the per-core ratio limit, not the turbo ratio limit. And that's because technically the granular ratios aren't set directly, but instead downbinned from the per-core ratio limit. For example, let's say you set a granular ratio of 60.16x. In that case, the per-core ratio limit is set to 61x and then downbinned by 5 steps of 16.67 MHz, which is 100 MHz divided by 6. That is important to keep in mind in case you're also using other ratio configuration technologies. It's also important to keep this in mind when you're using adaptive voltage mode, because the adaptive voltage maps to the OC ratio. In OC strategy number 2, I already briefly touched on overclocking thermal velocity boost. Basically, this technology allows us to downbin the turbo ratio limit or the per-core ratio limit when the CPU operating temperature exceeds a certain threshold. This is a pretty useful tool when you're running into stability issues in heavy all-core workloads. Specifically, I found that the P cores can run at 5.6 GHz in light all-core workloads, but would crash when running heavier workloads. So, by setting an OCTVB downbin of 1 for when 7 or more P cores are active at a temperature of 70 degrees or higher, I get the best of both worlds. 5.6 GHz for all cores in light workloads, and 5.5 GHz when the workloads get too tough. Advanced voltage offset, more commonly known as the VF points, is a tool that's available for each of the individual P cores and every E core cluster. There are 9 available VF points for each P core, 8 of which are fixed to a specific ratio. That ratio is the same for all P cores. There are also 7 available VF points for each E-core cluster, 6 of which are fixed to a specific ratio, which is the same for all the E-core clusters. The final VF point is mapped to the OC ratio, which is the P-core or E-core cluster per-core ratio limit. If you use granular ratios, keep in mind that those are downbinned from the next full ratio. In other words, the OC ratio can never be a granular ratio. You can set a negative or positive voltage offset for each of these VF points. I'll cover how I use the VF points for this particular CPU in a couple of minutes. As I already mentioned in overclocking strategy number 2, overclocking Arrow Lake CPU cores isn't without a struggle. Fortunately, the Intel CPU overclocking toolkit is one of the, if not the most comprehensive tuning tool available in the industry. So even if we're not going to be able to get the frequencies up very high, it's not for a lack of tools or for a lack of trying. We'll approach the fine tuning in the same way like we did the basic tuning. So we first pick the voltage, then we check for 1T stability, and then we check for all-core stability. From earlier testing, it's clear that the P-cores don't scale much with voltage beyond the maximum default frequency of 5.7 GHz. That said, I still increased the voltage at VF.8, which is for the 57x ratio, by 50 mV in the hope to push the non-favored P-cores closer to the 5.7 GHz mark. For the E-cores, I first increased the voltage limit to its maximum allowed limit and then increased the adaptive voltage to 1.35 volt. That's 100 mV more than what we used in OC strategy number 2. I use a similar testing process and benchmark selection for fine-tuning the per-core stability, and the same limitations still apply. It's the AI benchmark that's limiting our per-core ratio limit. By offsetting the P-core VF.8 with an extra 50 mV, we increase the voltage at 57x for every P-core. That gives us enough headroom to further increase the non-favored P-cores to 5683 MHz and the two favored P-cores to 5716 MHz. I want to emphasize two things about this configuration. Remember the rules for the granular ratios. The ratio is downbin from the per-core ratio limit. So when we set 56.83x for the non-favored P-cores, it's running at the voltage mapped to 57x, which we increased by offsetting at VF.8. Also remember the rules for adaptive voltage. The voltage for the favored P-cores running at 57.16x is defined by the 58x ratio. That's mapped to VF.9, which we configured by setting the global adaptive voltage to 0.6 volt. Since 0.6 volt is below the voltage for the VF.8, the voltage for 57.16x will be the same as for 57x. The additional 100 mV for the E-cores gives us another 100 MHz. One of the E-core clusters seems to be a little bit better than the others and can run 5.3 GHz at a lower voltage. By setting its per-core ratio limit to 54x, I can lower the effective interpolated voltage at 5.3 GHz. Alternatively, I could have configured the per-core adaptive voltage for that E-core cluster. To improve the stability and performance in all core workloads, I rely on advanced voltage offset and overclocking thermal velocity boost. The advanced voltage offset lets me undervolt the P-cores and the E-cores in all core workloads. The E-cores in particular could undervolt quite significantly at VF.6, which matches the 46x ratio. By lowering the voltage by 75 mV, we negate some of the effects of increasing the adaptive voltage to 1.35 volt. The P-core undervolting headroom is a lot less impressive. Still, I was able to reduce VF.5 mapped to 53x by 50 mV and VF.6 mapped to 55x by 15 mV. The last thing I did was use OCTVB to reduce the P-core frequency in all core workloads by 1 bin from 57x to 55x when the temperature exceeds 70 degrees Celsius. This was necessary because I could run 56x in lighter workloads, but it would crash in heavier workloads. Upon entering the BIOS, The CPU boost frequency with one active P-core is 5716 MHz. The average boost frequency gradually trails off to 5600 MHz when all P-cores are active, and to 5200 MHz when all P and E cores are active. In single-threaded applications, 2 P-cores can boost to 5716 MHz, and 6 can boost to 5683 MHz. Every E-core can boost to 5.3 GHz. We ran the benchmarks and checked the performance increase compared to the default operation. While the additional voltage doesn't add much P-core top speed, the additional 100 to 200 MHz for the E-cores and the undervolt for the P-cores and the E-cores helps lift the performance in multi-threaded workloads. The GeoMean performance improves by another 0.57 percentage points, and we get a maximum improvement of plus 40.51% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5455 MHz with 1.216 volts, and the average CPU E-core effective clock is 5001 MHz with 1.199 volts. The average CPU temperature is 104 degrees Celsius. The average CPU package power is 369.6 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5419 MHz with 1.218 volts, and the average CPU E-core effective clock is 5000 MHz with 1.219 volts. The average CPU temperature is 103 degrees Celsius. The average CPU package power is 365.3 watts. In the fifth overclocking strategy, I have a look at tuning the memory, increasing the frequency, as well as adjusting the timings. For that, I rely on the ASUS memory presets, as well as do some manual timing adjustments. ASUS memory presets is an ASUS technology that provides you with a number of memory tuning profiles for a variety of memory ICs. On the ASUS ROG Z890 Apex motherboard with BIOS 1401, there are 8 presets available for Hynix 2x16 and 2x24GB memory. Since I'll be looking to improve the memory timings as well as maybe increase the memory frequency, I load the Hynix 9000 1.55 volt 2x16GB A-die profile. Here's the configuration of that profile. It's of course not a given that just copying over the timings will work with any Hynix memory kit. So before I try to increase the frequency, I first check if these memory timings also work with DDR5 8000, which I've been using in previous overclocking strategies. Checking for memory stability is a bit of a hot topic in the overclocking community because different communities will use different yardsticks. I think that using Karhu is the meta currently, but it used to be Memtest. Personally, I always use the OCCT memory stress test for 1 hour because I found that if it passes that stress test, usually it also passes anything else that I throw at it. But if you want to use a different stress test, that's okay too. Stability means different things to different people. Then I try to increase the frequency to DDR5 8600. To achieve stability, I had to adjust a couple of memory timings. Here's my final memory configuration. After the memory tuning, our AIDA64 performance improved quite significantly. We got about plus 60% extra bandwidth and plus 25% better latency by enabling XMP 8000. Tuning the data fabric improves the write bandwidth by 17% and improves the latency by 7%. Tuning the memory then adds another 12% extra write and copy bandwidth while maintaining the same latency. Upon entering the BIOS, We reran the benchmarks and checked the performance increase compared to the default operation. Tuning the memory timings and adding a little bit of frequency doesn't have the enormous impact some would expect. However, it's nonetheless interesting to still see the performance improve, especially in multi-threaded workloads. The geomean performance improves by another half a percentage point, and we get a maximum performance improvement of plus 42.73% in PY prime. In a final overclocking strategy, we have a look at power gate mode and see if it can improve our P-core and E-core overclock. In power gate mode, all DLVRs tied to the VCC-IA voltage rail are bypassed, and the connected IP blocks are powered directly by the VCC-IA voltage rail. Power gate mode is basically how the VCC-IA voltage rail worked on previous generation Raptor Lake processors. For Arrow Lake it works, but it's a little bit complicated. To make a long story short, when the P-cores, E-cores, and ring request their voltage to the CPU PCU, they account for a ton of other compensations including the voltage droop, AVX guard band, thermal velocity boost voltage optimizations, and so on. The result is that the actual voltage provided from the VCC-IA voltage rail to the IP blocks is relatively high. For example, here are the voltages with an Arrow Lake CPU running a light all-core workload. We can interpret this as follows. The P-core, E-core, and ring request a voltage to the PCU to ensure it'll run at 1.15, 1.05, and 1.1 volt respectively. The PCU then adds compensation for the load lines, CEP, TVB, AVX, and so on. At the end of the calculation, the PCU determines the VCC-IA voltage rail should provide 1.43 volt input voltage to the DLVRs. If we were to switch to power gate mode, but maintain the same mechanism for calculating the required voltage, then the VCC-IA voltage rail would effectively provide 1.43 volt to the P-cores, the E-cores, and the ring. That's obviously way too high and would quickly result in an overheating system, but this would be how the voltage was configured on previous generation Raptor Lake processors. Fortunately, there's another way to approach power gate mode, and that's ignore all of the ISVID stuff and program the voltage output directly over PMBus. That's the traditional way of overclocking. That's how we did it 10 years ago. Basically, you set a fixed voltage output and then you manage the voltage in all core scenarios with an appropriate VR load line. Before we continue, we have to talk about the elephant in the room. Power gate mode will not be available for ambient overclocking in the future. At least that's Intel's plan. The real reason is not known, but presumably it's got something to do with power gate mode enabling voltages much higher than the DLVR limits. That could, in theory, cause harm to the CPU. My opinion on the matter is very clear. Power gate mode is just like any other overclocking technology. It will make your processor run out of spec, it will void the warranty, and it may cause damage to your processor. Now, the decision whether to accept that risk should be up to the customer. It should be up to the person who paid money to buy the CPU. We don't need Intel or any other vendor to tell us what we can and cannot do with the product that we purchased. With that out of the way, I also want to briefly touch on why power gate mode is still available on some motherboards with newer BIOSes. To keep it short, while the latest firmware package from Intel doesn't officially allow for power gate mode to be enabled, since it was available on older code, it's possible for motherboard vendors to rely on older firmware to retain support. Think of it like the support for non-K overclocking or AVX512 on Alder Lake processors. The tuning process for power gate mode is very similar to what we did in OC strategy number 2 and OC strategy number 4, with one major difference. Instead of relying on the CPU VF curve, we program the voltage directly in the voltage regulator and then use an appropriate load line to manage the voltage in all core scenarios. For my system, I picked 1.375 volt for the VCC-IA voltage rail. The reason is that this is about the voltage limit for the E-cores, and I wanted to see what we can get from a system if power gate mode were officially allowed, but with strict enforcement of the voltage limits. First, we try 1T stability. Similar to what we did in OC strategy number 2, we can first set the turbo ratio limit to a high enough value like 60x, and then use the per core ratio limit to check stability for each P core and E core cluster. With 1.375 volt static voltage for the P cores, I could increase all except one P core to 5.8 GHz. However, that's only possible if I make extensive use of the OCTVB downbinning. Under a high load with temperatures exceeding 70 degrees Celsius, the maximum frequency is only about 5.6 GHz. The E-cores can reach about the same frequency as with DLVR, meaning we get about 5.2 to 5.3 GHz for the various clusters. The crucial part about PG mode is selecting an appropriate VRM load line so that you don't have too much voltage and therefore too hot of a CPU when you hit heavy all-core workloads. The process to figure it out is pretty simple. You set the turbo ratio limit for all core to the maximum per core ratio limit and then check stability. If it's unstable, you can increase the VR load line. If you hit TJ max, you can try reducing the VR load line or reduce the turbo ratio limit. In my case, I opted for level 6 CPU load line. At a set voltage of 1.375 volt, that gives me about 1.25 volt in a heavy all-core workload. Once you've chosen the output voltage and the load line, it's a matter of matching your CPU ratios and the turbo ratio limits according to the slope of the load line. This is a bit of trial and error as the P cores and the E cores put different load on the VRM. With one active P core, the load line drops it to 1.34 volt. With 4 active P cores, the voltage is 1.32 volt. And with all 8 P cores active, it's 1.29 volt. On the contrary, 8 active E cores only drop the voltage to 1.32 volt. And even 6 active E cores don't drop the voltage as low as having 8 P cores active. I found that there was little difference between DLVR and PG mode when it comes to all-core stability, so I stuck with the same settings. 5.6 GHz for the P cores and 5 GHz for the E cores. Upon entering the BIOS, The CPU boost frequency with one active P-core is 5.8 GHz. The average boost frequency gradually trails off to 5.6 GHz when all P-cores are active, and to 5.2 GHz when all P and E cores are active. In single-threaded applications, 7 P-cores can boost to 5.8 GHz, while one can only boost to 5.7 GHz. 2 E-core clusters can boost to 5.3 GHz, and the other 2 boost to 5.2 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. While power gate mode isn't officially supported anymore, my experience proves that it definitely has a place in Intel's overclocking toolkit for ambient overclockers, even if the strict voltage limits would be enforced. For example, in my case, I could quite easily get pretty close to the performance for a maximum DLVR tune, which took weeks to figure out. Our PG mode performance even beats the best DLVR configuration in some heavy all-core workloads like Y-Cruncher and AI Benchmark. The geomean performance regresses by 0.36 percentage points, and we get a maximum improvement of plus 44% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5,482 MHz, and the average CPU E-core effective clock is 5,000 MHz with 1.249 volts. The average CPU temperature is 104 degrees Celsius. The average CPU package power is 311.6 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5,500 MHz, and the average CPU E-core effective clock is 5,000 MHz with 1.26 volts. The average CPU temperature is 97 degrees Celsius. The average CPU package power is 288.2 watts. Alright, let's wrap this up. The Core Ultra 9 285K is the flagship Arrow Lake CPU, and it certainly feels like Intel tried to squeeze every little bit of frequency and performance out of the chip. It's one of the most difficult chips I've ever had the pleasure of tuning. On the P-core side, there's really limited overclocking headroom, and also it doesn't seem to scale with voltage that much. So what you're left with is trying to get the non-favored P-cores as close as possible to 57x, and then try to squeeze a little bit more frequency out of the favored P-cores, which are already running by default at 5.7 GHz. On the all-core tuning side, you can get an extra 100 or 200 megahertz, depending on the use of thermal velocity boost. On the E-core side, there's a little bit more headroom, so there you can get a couple of hundred of megahertz, but once again, you have to rely on the turbo ratio limit to configure the E-core ratio in a variety of scenarios to get the most out of the CPU. The ring, again, is very similar to the P-core. Very little limited overclocking headroom, and it doesn't scale with voltage. So on the 285K, probably you get about 4.2 gigahertz. On the memory subsystem side, and here we include NGU D2D and the memory itself, actually there's quite a bit of extra frequency available. So you can overclock the NGU by maybe 600 or 800 megahertz, the D2D by 1.5 to 1.7 gigahertz, and memory overclocking is really easy on Arrow Lake. Like, it was pretty easy to get all the way up to 8600. And combining everything, even though the frequencies of the CPU cores aren't really increased that much, you actually can squeeze still quite a bit of performance out of the CPU. We're not talking about 20% increases, but 5 to 10% or even up to 30% in certain memory-dependent all-core workloads is certainly possible. Anyway, that's it for this video. I hope you enjoy it. I want to thank the patrons and the YouTube members for their continued support. If you have any questions or comments, feel free to drop them in the comment section below, and see you next time.